My name is Cynthia Brazel, and my background is in marine and medical microbiology, and I have experience with biofilm prevention and removal in water and on surfaces. In this presentation, I will talk a little bit about the problems associated with contaminated water, mainly drinking water, and outline some treatments. Before I begin, I think that this slide puts the impacts and the potential of safe drinking water into perspective. In developing countries, 785 million people lack access to safe water, and a cumulative of 200 million hours each day are spent collecting water, and this takes away from work, school, and family. Universal access to basic water and sanitation would result in over $18 billion in economic benefits each year from avoided deaths alone. In developed countries, the use or overuse of toxic chemicals creates toxic residues or disinfecting byproducts that impacts the health of people, the environment, and leads to bacterial resistance. The US CDC put out this list of the top causes of outbreaks in public water systems in the US. In the EU, this list is very similar. It includes bacteria, parasites, and viruses. The top causes are Giardia, Legionella, and norovirus. These organisms can cause severe gastrointestinal issues and fever, which leads to dehydration, or serious types of lung infections or pneumonias. I also want to point out that copper is on this list, and I will talk about this again in regards to bacterial-induced corrosion. Biofilm is a slime formed by bacteria and other fungi and other organisms on surfaces in water. In this diagram, you can see the stages of development of a biofilm. First, bacteria attach to the surface, they grow, and they start secreting the biofilm slime, which is like a sticky glue. And after the biofilm matures and thickens, there's another stage where bacteria are dispersed into the water again. Often when pipes become clogged, it is a result of a big chunk coming off. For potable water systems, biofilm is a major problem that occurs at the sites where water is traveling from a local distribution plant to end users. Biofilm is also a big problem in cooling towers, closed-loop systems, desalination plants, and wastewater pipes. This diagram shows that when a thin layer of biofilm forms, a biocide treatment is added and may be able to kill that thin layer of organisms. But when the biofilm builds up, the biocide is not able to penetrate and kill the underlying cells. In this diagram, you can also see pathogenic bacteria in red. Those bacteria with resistance genes can easily transfer their resistance to other cells, making the biofilm even more difficult to remove. Because of these aspects, a biofilm is very difficult and costly to remove because it's resistant to the normal doses of disinfectants used to treat water. The pictures on the left are biofilms in water pipes, and you can see it can be very thick. We've spoken to companies that have had to shovel the biofilm out of their pipes. In addition to the contamination, biofilm slows the flow of water. This increases energy consumption and adds costs. The picture on the top is from NASA and the potable water system on the International Space Station that we had a project with. In that case, the bacteria had become resistant to silver, and silver is NASA's antimicrobial of choice because of its safety profile. Biofilms in shower heads are associated with the spread of non-TB mycobacterial respiratory infection. Legionella biofilm in air conditions, cooling towers, jacuzzis have been associated with major outbreaks. Biofilm has become such a problem in hospitals that in the US, they've removed the sinks from doctors' offices and patients' rooms because the pathogenic bacteria can live in the sink pipes and reinfect patients. In addition, microbial-induced corrosion is associated with biofilm. It's due to the bacteria in contact with the surface under the biofilm that causes serious corrosion. In addition to damaging the pipes, when this corrosion occurs on copper pipes, it can release high amounts of copper into the water, exceeding the maximum allowable concentration. These are the most common water treatments used. The most common are biocides and dispersants. For the next part of the presentation, I will focus on biocides, biodispersants, UV light, and ultrasound treatments. Since every system is different and has different contaminants and different pH and specs, there is no one solution that fits every system. Here I will outline the most commonly used biocides that are oxidizers, that work by oxidizing essential parts of microbes. Chlorine is the most common treatment for systems below pH 7.8. A sustained high dosage is needed to penetrate biofilm. Chlorine gas, however, is hazardous, and chlorinated organics are suspected carcinogens. Chlorine is also corrosive to stainless steel and copper. Bromine is commonly used for systems above pH 8, however, it also has hazardous halogenated byproducts. Ozone is effective, however highly reactive, unstable, and has to be produced on site. Peracetic acid kills quickly and is known to disrupt sulfur bonds, so it can break up proteins and peptides, and it penetrates cells better than hydrogen peroxide and some other oxidants, which may be why it kills so quickly. However, microbes can eat it, removing it from the water. Chlorine dioxide is another treatment, however, it is only effective against targeted pathogens and decomposes into halogenated disinfectant byproducts. Hydrogen peroxide is effective, however, very high concentrations are needed, and it's a very strong irritant at concentrations above 5%, and it creates a storage hazard. Iodine is another oxidizer that has been historically used, but there are health concerns associated with people with thyroid disorders. Here I will outline the non-oxidizers and biodispersants and things to consider when using them. Quaternary ammonia compounds are commonly used and they are effective. However, they also create toxic nitrosamine disinfectant byproducts. Another problem associated with quats occurs when equipment is washed down. This is a problem because if the quats enter wastewater systems, they can poison the good aeration bacteria. Anionic and ionic surface active agents are effective against targeted pathogens only, and some are toxic to aquatic life. Silver ions, silver nanoparticles, and copper silver have broad spectrum antimicrobial activity against bacteria, fungi, and some viruses. Silver is most commonly used in water filters, and copper-silver ionization technologies are effective preventative measures against the colonization of Legionella in hospital hot water systems. However, with the increased use of silver in systems, there is a rise in resistance to silver. Enzymes are often used in wastewater treatments, but they can also be used to target biofilm. In that case, they essentially eat the glue that holds the biofilm together, but because of their high cost, they are primarily used to clean filters. Blends are also created combining surface active agents together and surface active agents with oxidizers. Acor specializes in blends and non-toxic solutions. Next, I will talk about two treatments where no chemicals are added. Ultraviolet UV light kills bacteria and viruses. It's advantageous because it kills without adding any chemical to the water, but it is limited because it has very low penetrative capabilities, so it needs to be used in a filtration system. High-power ultrasound creates microbubbles, and high-energy shock waves have been used to treat wastewater and has been shown to be beneficial in conjunction with membrane filtration. With membranes, the ultrasound creates bubbles, and when these bubbles form and burst under different pressures, they release energy and cause vibrations that loosen particles on the surface membrane. There are also sonicators that can be attached to the outside of pipes that can then dislodge biofilm inside the pipes. Technologies to monitor biofilm are showing to be beneficial. This is an example of a biofilm monitoring system that uses real-time probes that are inserted into the water pipes. The probes are able to detect when bacteria first settle on a pipe, indicated by the rise in the red line on the graph. The sensors can distinguish between biofilm and scale deposits. The rise in the biofilm then tells the user when a higher dose of a treatment or a different treatment is needed in the system. This allows the user to check the efficacy of the cleaning. A system like this can also prevent the overuse of biocides. I am happy to answer any questions by email, and please contact me if you have any interest in treatments for biofilm in water, on surfaces, microbial testing services, or biofilm monitoring probes. Thank you.